and she agreed to help us out. The second announcement is that following up the evaluation form that we sent out last week, I think, we decided to record the talks. However, we only will record the talk. We don't record the discussion later, so that people are not scared to ask questions later during the discussion. However, if you have any questions during the talk, any clarifying questions, don't hesitate to ask them. They will be just recorded afterwards. And we will put the video later on YouTube, so you can watch it later. Unfortunately, we didn't get a strong signal whether we should postpone the seminar to another time slot or not. So people seem to be quite happy with the time slot that we have right now. So that's why we decided to stick to 4 p.m. We might reevaluate this maybe a couple of months, depending how the recording works. So with that, it's my great pleasure to introduce our today's speaker, Xuanyi. He's a PhD student at the University of Sydney. Xuanyi is also author of NAS Bench 2.1, which I think many people here know and probably also do use often. And he's going to talk about extending the search from architecture to hyperparameter hardware and system today. So with that, the stage is yours.
Okay, thanks for the introduction from Aaron, and thanks for everyone for this presentation. So today I will talk about extending the search from architecture to hardware and to hyperparameter hardware and system. So let's first have a look at this figure. It's from the Efficient NAS SML 2019 paper. It shows how automatically discovered architecture outperforms manually designed one. And this outperforming performance, it also achieved as Efficient NAS v2 published about 1 week ago on Archive. So automatically discovered architectures, it still consistently outperforms the manually designed architecture for a long time, since 2017, I think. Also, if we have a look at the NAS paper published online available, so the NAS paper, they grows very fast. The number of NAS papers rapidly increased. This also shows a tendency from manually designed architecture to neural architecture search. So what is neural architecture search? Basically, neural architecture search is composed as 3 main components. The first one is child programming. It is, for example, it could be train a ResNet on ImageNet datasets. And then we will extend this child program to a search space. In a search space, it might be we can replace all the convolutional layer in your ResNet, be 3x3 convolutional layer or 5x5 convolutional layer or separable convolutional layer of these candidate operations. They can form a new model, and every new candidate model, they all together from your search space. After you have the search space, you can select a search algorithm, maybe PPO for reinforcement learning or Hyperband or BOHB, to explore your search space. By exploring, it means you can use your search space to sample a candidate child program and then execute this child program. For example, you sample a model and then you train this model on ImageNet and then evaluate this model on ImageNet. And then you can have some evaluation metric, and this evaluation metric can be served as a feedback to further improve your search algorithm to improve the quality of your next sampling. So this is basically a neural architecture search algorithm. And what is important to neural architecture search algorithm in these 3 components? Here, basically, in the past 4 years, people mainly focus on the study of these 2 things. The first one is search space. So there are two very popular search spaces called NASNet search space and the MB-conv based search space. For example, you can replace the kernel size and expansion ratio in MobileNet v2. We call it MB-conv based search space. And also people also study how to effectively and efficiently exploit a search space. Basically, these lines goes to different search algorithms. For example, you can use Bayesian optimization or PPU or reinforcement learning or evolutional or differentiable based search. However, at today and now, the NAS performance is saturated. On both NASNet search space and FB-conv based search space, if you have a look at the recent papers, you can find that the performance of different papers, actually improves very little compared to the popular NAS algorithms on these two search space. Especially for the search space, if we have a look at our recent paper called NAS Bench, in this benchmarking paper, it's an upgraded version for NAS Bench 2.1. We proposed a new size search space. It basically searching for every number of channels in each layer in your model. So we call it size search space. It aims to search for a good model size. And on this search space, if you only searching for the model with better accuracy, actually different search algorithms, they can quickly find almost close to the best model on this search space. This is said that if you if you carefully design your search space, maybe your model can quickly converge on your search space. And on the existing popular search space, different NAS algorithms, they have explored it for a long time, and the NAS performance is really saturated. And on the other hand, for search algorithm, on our benchmarking paper, we also find that if you are using different search algorithms, for example, for both multi-trial based searching algorithm, regularize the evolution or reinforce or random search. Given sufficient training time, this multi-trial search algorithm, they can also converge to a similar position. And also for the popular weight sharing based searching algorithms, if you apply some well-known NAS tricks to improve the quality of your shared weights, they can also converge to some similar position, finding the neural architecture with very similar performance. This is also our observation that different NAS algorithms, if you carefully tune them, actually the performance is also saturated. And also we find that NAS might be a suboptimal solution in terms of the broader AutoML. So if we have a look at this figure again for the recent Efficient NAS v2 model, although its performance is very good, it's very great, it achieves a new SoTA performance, but the performance is not purely achieved by NAS. It combines both NAS search model with some manually designed training strategies. And also, if we have a look at the performance gain for every component, every improvement in the paper, we can find that maybe the manually designed training strategy is the biggest help in Efficient v2. This is said that maybe we need to move our focus from search space and search algorithm to the child program. We need to consider how to make your child program being better. And also, another observation in our recent AutoHAS work is we find that we randomly sample some candidate architectures from a search space built up on MobileNet v2. And we also randomly sample some hyperparameters. We use this randomly sampled hyperparameter to train these randomly sampled architectures. And we find that under different hyperparameters, the architecture ranking, they are very different. And here we pick up two models from our experiments and two hyperparameters. We can see that different models, they prefer different hyperparameters, and especially under different hyperparameter, the model ranking can be different. So if you only use a single hyperparameter and the discovered model, they might be good at these hyperparameters, but when you switch to another hyperparameter, your results might be a different one. So this also indicates that the NAS is a suboptimal solution. This motivates us to propose jointly searching for both hyperparameter and architectures. If we can consider both hyperparameter and architecture jointly, maybe we can find a better trained model. So as our main goal is not to discover a single architecture, our main goal for AutoML is to deliver a good trained model, so that if we jointly searching for both hyperparameter and architectures, probably our final trained model can be better. So that we propose AutoHAS is an efficient framework to be able to jointly searching for both hyperparameter and architectures. Here we summarize a table to compare AutoHAS with previously published hyperparameter optimization or NAS papers. So basically, for some of the hyperparameter optimization method, they are specifically designed for some hyperparameter, not all hyperparameter. For example, one recent paper on Accelerator 2018, they are specifically designed for learning rate. And for some other gradient-based hyperparameter optimization method, they cannot be applied to some non-differentiable hyperparameters, such as the data augmentation policy or the dropout ratio. And also, our AutoHAS can be used for searching for all of these hyperparameters and architectures. Actually, our AutoHAS is capable of searching for most of the hyperparameters, and also it's very efficient. So let's have a look at these details. What does AutoHAS look like? So here is the framework of our AutoHAS. Basically, we first design an AutoHAS controller to draw the underlying distribution of both architecture space and hyperparameter space. We can use this AutoHAS controller to sample some candidate architecture and candidate hyperparameters. After we sample this candidate architecture and candidate hyperparameters, we need to evaluate how good it is for this architecture combined with this hyperparameter. So that we created a temporary weights, we call it W star, subscribed by alpha, for this sampled architecture. This temporary weights, W star, it is calculated by applying the sampled hyperparameter on the sampled architecture by one or multiple gradient descent steps. And after we calculate this temporary weights, we can use it to compute the accuracy on a batch of validation data. And then we can use this validation accuracy to further improve the AutoHAS controller, so that following these blue lines again and again, the AutoHAS controller can be optimized very well. Then it can draw in a good distribution for architecture and hyperparameter. Then we can use it to select the best one. And note that this framework is very general. We can not only use, so here we use validation accuracy to improve the AutoHAS controller. We can use reinforcement learning algorithm to do the optimization. Well, alternatively, we can also use the popular differentiable-based searching algorithm to do it. For example, we can switch the validation accuracy to validation loss. Then we can calculate the gradient from this validation loss to the controller to backpropagate to it to optimize this controller. So it's very general. You can plug in both reinforcement learning or differentiable based search or Bayesian optimization. And on another iteration, so if we want to use the temporary weights to accurately estimate the quality of your sampled architecture and sampled hyperparameter, we need the initialization of this sampled architecture, the initialized weights for this sampled architecture to be good. So we need this W subscribed by alpha to be good. In this, to achieve this, we need to follow the red line to use the training loss to update the W. And we also use weight sharing technique to share the weights between different candidate architectures. It's similar as the previous weight sharing based NAS algorithm. In short, you could have a supermodel to cover all the candidate architectures. And after you have this supermodel, you can share the weights between the supermodel with its subnetwork, where each subnetwork is a candidate architecture. So that by using this weight sharing technique, our AutoHAS can be very efficient. And using this framework, our AutoHAS can be very general to be able to handle most kinds of hyperparameters. And later we will show what kinds of hyperparameters we have tried. So first we compare the popular differentiable based search and reinforcement learning based search in our AutoHAS. We use MobileNet v2 as our baseline model and we train it on the ImageNet datasets. We discovered that by using differentiable based searching, we need almost 6 times of the memory cost compared to training a single MobileNet v2. And by using the reinforcement learning based searching in AutoHAS, we can use about less than 1/10 of the memory cost and almost a similar time cost for compared to training a single MobileNet v2 on ImageNet. So that in our following experiment, we choose reinforce for our search algorithm. And here is how AutoHAS can improve the state-of-the-art models. We choose the 2 popular models, Resident 50 and Efficient B0. We searching for the Resident 50, we do not search for architectures. We only search for the learning rate, weight decay, and dropout ratio, these 3 hyperparameters. And we find that AutoHAS can improve its accuracy by 0.6 on ImageNet. And for the Efficient B0, we use it as our base model, and we're searching for the expansion ratio, the kernel size, and also some hyperparameter configurations, as well as the learning rate and the drop path ratio for Efficient B0. And by applying AutoHAS to jointly searching on this architecture and hyperparameters on Efficient B0, we find that we can improve the accuracy by 0.7. Here is some visualization results for AutoHAS. We visualize how the dropout ratio searched by AutoHAS looks like. We're searching for the dropout ratio in EfficientNet, and here is some visualization results. And here is some visualization results for the learning rate when we use AutoHAS to searching for the learning rate for different MobileNet models and ResNet. So that we find that different mobile models, they may prefer different kinds of learning scheduler. For example, for the MobileNet v2 T0, it's a very thin network. We find that it prefers a very high peak value for your learning scheduler. And the And the dashed black line is our default learning rate scheduler. It's the warm-up with cosine decayed learning rate scheduler. It's a very strong baseline, but our AutoHAS can still find better learning rate scheduler for different models. And we also apply it to the NLP task. For the BERT model, we usually pre-train the BERT model on some proxy tasks, and then we will fine-tune the BERT model on some downstream applications. So for the fine-tuning, we have some hyperparameters, for example, the learning rate and the weight decay. We use AutoHAS to searching for the learning rate and weight decay for these fine-tuning tasks on squad 1.1. And here is the results for our AutoHAS-discovered hyperparameters. As you can see that AutoHAS consistently improved the EM score and F1 score. And also here is we apply AutoHAS on 5 more different datasets and on different search space. When we use AutoHAS to separately searching for weight decay, mix-up, and architecture, we can find that it also consistently improve the accuracy compared to the baseline model. And also when we jointly searching for mix-up with architectures, the accuracy on some datasets it improves, but on some it's actually worse than searching for a single hyperparameter. But still similar, yeah. And we also apply AutoHAS to jointly searching for weight decay and mix-up ratio on these 5 datasets. It achieves the best performance. So this actually raises a question. It seems that joint searching does not actually improve a single search, so that we apply another algorithm, algorithm to sequentially searching for both for different hyperparameter and architectures. Sorry, it seems one slide is missing here, but I can describe the results. So by sequentially search, it means that we sequentially searching for weight decay, mix-up ratio, and architectures, and we find that for this sequential search, it will consistently improve compared to searching for a single hyperparameter. And for joint search, it's on 3 datasets, it improves the performance compared to the sequential search. But on 2 datasets, it is worse. We think that it is because the joint searching of architecture and hyperparameter is still a very challenging task and still have many things to explore. And also here we compare AutoHAS with some HPO methods, and compared with multi-trial based searching, the basic Bayes optimization, and random search. AutoHAS is much more efficient because that we use weight sharing technique. So under the same amount of computational resources, AutoHAS can traverse more candidate architecture and hyperparameters than Bayes optimization and random search. And compared with some other gradient-based searching method, our AutoHAS improves their accuracy by a little compared to IFT, and improves many compared to HED. So this is basically our recent work on the joint searching of hyperparameter and architectures. So that by using AutoHAS, you can jointly searching for both architecture and many hyperparameters. And what is else? What else could we also include in our search space to further improve the performance? Here is our another direction to explore is the hardware accelerator, so that in all the previous work, in all the previous experiments and most works, people only use the same devices, explore the NAS algorithm or HPU algorithm on the same hardware. Maybe you can searching for different latency constraint, but your target hardware is still a single one, either on CPU or GPU or some other GPU devices. But here we argue that we can do better if we jointly searching for both hardware accelerator and neural architectures. Here we show an illustration on why it can achieve a better Pareto optimal. So on the left hand, if you only have a single accelerator configuration, maybe you can find some good models by NAS algorithm on this Pareto frontier. But on the right hand, if you have different kinds of accelerator configurations, and you include this accelerator in your search space, you can have a better Pareto optimal solution by this black dashed line. So this is our key motivation. And also in many industrial-based applications, for example, the Waymo self-driving cars, the task is specific to maybe object detection or object segmentation. Maybe a model might evolve, but the task is still constrained to this to some vision-based applications. And for this vision-based model, actually your low-level operations, they will keep similar between each model, so that if you're using the general hardware devices, for example, the CPU or GPU, they are designed to make every model, the expectation of every model to be faster and effective. But if in a specifically constrained applications, the self-driving cars, then since the application is constrained, we only need to make some specific model to be good and ignore other models. In this way, the CPU or GPU devices might be a suboptimal solution in these constrained applications, constrained scenarios. And also, if we're jointly searching for both architecture and hardware, the previous AutoHAS will not work, because for different hardwares, your candidate architecture and candidate hyperparameters on different hardware, they might perform differently, but their accuracy will be the same. So we need to include more metrics, for example, the energy metrics, the latency metrics, to be included, and also the temporary weights here, W star. It only reflects the quality of your architecture and hyperparameters, but it cannot reflect the quality of your hardware. So we need some new algorithms. So here, when we include both architecture and hardware in your search space, so what's the difference between previous hyperparameter? So in the AutoHAS work, the hyperparameter mainly refer to some hyperparameters that can affect your training procedure. But here for the hardware, we can, in some works, it also considered it as a hardware hyperparameter. It usually could be some dimensions of your chip, the size of a chip and some number of units, the registration size, some memory size, such as these things. And here is a general framework for the joint architecture and hyperparameter, for the joint architecture and accelerator search. So here is two solutions to do the joint searching. One is to using the multi-trial based searching algorithm. You can regard the configuration, one configuration of hardware and the acceleration and architecture as a black box for evaluation. so that you can apply any multi-trial-based searching algorithms to it. And another way is to apply the weight sharing technique. For the weight sharing technique, here we need to design a neural predictor to take the hardware configuration as input and then output some latency or energy as a estimation to accelerate how this hardware work well, because that for one-shot based method, for the weight sharing based method, every iteration you need to be very fast. But for a hardware, if you want to simulate architecture on hardware, it costs more than minutes or even to 1 hour. So it's very expensive compared to forward the architecture by one iteration. So we need to design a neural predictor on it. And actually we explored both of these two directions by using both multi-trial based searching algorithms with some with Bayesian optimization. With reinforcement learning, and also explored how the weight sharing technique can work on this joint architecture and acceleration search problem. And here is some results compared between the multi-trial based searching algorithm and the one-shot based searching algorithms on this joint hardware and accelerator search. It can perform very good compared to previous NAS only based method. And between both of these two methods, multi-trial and one-shot, actually the final search architecture do not have a very big performance, but compared with the efficiency, multi-trial based searching algorithm is less efficient than one-shot weight sharing method. Yeah, that's their pros and cons. But for multi-trial based, it's very flexible. You can apply it anytime you want. But for the one-shot method, if you switch to a different hardware configuration, you need to redesign your neural predictor for the latency and the energy, and then retrain this neural predictor. So it's less flexible compared to multi-trial based searching. And also we compare two strategies. The first one is phase-wise searching. For the phase-wise searching is that we searching for hardware accelerator only by using some popular models such as MobileNet V2, Efficient NAS V0. We find a good hardware on these models so that it can have some good latency and energy cost on these popular mobile-based models. And then we fix this hardware and then searching for the architectures on this searched hardware accelerators. And this is called phase-wise searching. It indicated as the dashed line. And another solution is the joint searching, jointly searching for both hardware and accelerators. Here is the results. As we can see that the joint searching on these tasks, it significantly outperforms the phase-wise searching. This also indicates that joint searching can find better solutions, and the phase-wise searching is somehow a suboptimal solution. And here is our final performance by using our joint architecture and hardware search. We can find a much better performance, a much better model in terms of the edge TPU energy compared with the previous popular Efficient NAS models. So that what is the next? After we explored searching for the hyperparameter, the hardware, the architecture, what's the challenge for AutoML currently? Our observation is that if we want to scale up AutoML horizontally and vertically, basically it equals to we design more AutoML algorithms and then apply AutoML to more applications. In both of these two directions, we need to improve the programming interface of AutoML. So let's take several seconds to consider how should you implement AutoHAS, the previously mentioned work, and our recent NAHAS work. What will you do if you implement it from scratch? And how many lines of code and how much time will it cost? And let's consider another example, a triple level search. Suppose we have some search space. We have a basic search space. It consists of some basic operations such as multiplication, additive, and square function. And we want to use these operations, these basic operations, to build an architecture search space, to build a better architecture search space. And then we use this architecture search space to discover a better architecture. What should you do if you want to implement such a triple level search problem? Is it a very challenging problem for the implementation? I think it is yes, based on the current PyTorch or TensorFlow libraries. This is why is it challenging? It's basically because that the current framework, the current algorithm implementations, they heavily coupled every components, the child programming, the search space, the search algorithm together. Since each thing is coupled together, if you want to improve or modify for some things, it's very hard. For example, here, if you have a residue block and if you want to re-implement this residue block, you want to modify the existing code of this residue block into a search space, what will you do? Basically, this is the typical style. If you want to improve it to be a search space, you add one hyperparameter configuration for input function and assign some attribute in these configurations to indicate different choices for the search block. But if you implement in this way, actually the child program and the child program and search space is highly coupled together. And what will you do if you implement the popular efficient neural architecture search algorithm in NAS? You basically replace the layer of MBCon with some switch layer. By switch, it means you can switch between different branches and in this 3x3 MBConf or 5x5 MBConf or 7x7 MBConf. So in this way, actually the search space and search algorithm, they are heavily coupled together. And what's for that algorithm, differentiable based searching algorithm, it's similar. You re-implement your MBConf layer with summed layer. It is heavily coupled together between search space and search algorithm. So that if we want to change the search space or if we want to change the search algorithm based on the existing code, it becomes very difficult. But if you want to scale up your AutoML algorithm to rapidly implement some new algorithm, we need to be able to fast switch between different search algorithms in different search space. As we call it, the fluidity of coupling. We need to actually decouple each of them. So that's our solutions to decouple, to make every coupling become a dynamic one. So compared with previous implementation styles or compared with previous libraries, basically it's like when you implement your AutoML algorithms, after implementation, you have a fixed building house. And if you want to change the door or window of this house, it's impossible. But here, if we can implement your AutoML algorithm like a Lego brick, you combine each component dynamically, then in this way, if you implement like a Lego brick, you can easily switch between, you can easily change the door or window after you build it. So we call our new libraries as, so we introduce this dynamic style. We introduce this symbolic programming into AutoML. By symbolic programming, it's like you build everything, you build every code in your, you build every Python code like a Lego brick. You have some simple and unified interface, like a single Lego brick that you have unified to understand. By symbolic, it means this is some example code of symbolic that by using our library, by using our new library, you can assign a decorator on any existing Python objects, Python classes, and then these classes will be symbolic. Every input of its function will become an attribute for this class that can be very easily modified. So it becomes some unified stance of a Lego brick. And if you want to change your existing code by, for example, here we have a child program. It trains two convolutional layers that build a model, and we use Adam as the optimizer to train it. So on the left hand, this is an existing trainer you have already implemented in your code. This is the class of your existing trainer. And if you want to change the convolutional layer in this trainer to another trainer, what will you do? In the past, you need to copy this code and then modify the convolutional layer into your max pooling with the max pooling layer. But now we can change it dynamically. So that we can write a function, we call it swap function. Basically, we can replace this, we can call the function called rebind function with this swap function, and then it can replace every convolutional layer in this trainer, so that we can modify a Python class like the data. We can modify any Python class or object like how you modify the data. And here is how we switch between the child programming and the child program and the search space. It's similar like previous one. We have a static child program, the code trainer here, and we want to make it become a search space. Basically, what we do is to apply a swap function that replaces the convolutional layer with some one-off object, and then replace optimizer with another one-off that indicates its candidates. That's how we switch between the static child programming and search space. In this way, if you want to switch between search space, you just change another swap function. And here is how we express the AutoML algorithms. We express every AutoML algorithms like a follow function. For this follow function, its main components is called a sample function. It samples from the search space together with a search algorithm. Here, for example, we can have a hypertrainer. Here, a hypertrainer is a trainer that contains some one-off components. And by doing the sampling, it can sample a concrete trainer, and we can execute this concrete trainer to get some reward function. Use this reward function to feedback to improve your search algorithm. And how does this work? here is an illustration of how it works. So first we will have a hypertrainer. It basically equals to a search space, have some one-off. And then by using our symbolic programming, we can easily map this search space into an abstract search space, so that in this abstract search space, all the irrelevant components can be disregarded. For example, the specific choice in your one-off operator, we only need to know that for most black box optimization algorithms, we only need to know we want to choose from 3 choices, but it is not necessary to know what is the details within these 3 choices, so that we can map between, we can map from this concrete search space to the abstract search space. And we only let our search algorithms work on this abstract search space. They can do the sampling on this abstract search space and sample one concrete abstract child program. And then we can map back from this abstract child program to the concrete child program and do the training and evaluation. So this is how the sample works. In short, I will skip some slides. So here is how basically how our new libraries, we call it PyGlove, it's use the symbolic programming to improve your existing code, And here is some examples of after we use the symbolic programming, how the AutoML algorithm will be implemented as. And here is the results if you're using our new libraries, PyGlove. Suppose we have 3 search space. The 3 popular search spaces, like we're searching for the kernel size and expansion ratio of the inverted bottleneck unit in a mobile net v2 model. This is the first search space, we call it S1. And the second search space is we can searching for the number of filters in each inverted bottleneck unit in mobile net v2. This is the second search space, we call it S2. And for the third search space, it combines both S1 and S2, searching for both kernel size, expansion ratio, as well as the number of filters. So this is 3 popular search spaces in the existing NAS works. And also, suppose we have 3 search algorithms. The first 2 is random search and Bayesian optimization. It's a multi-trial based searching algorithms. And the third one is the white box optimization. It's the Efficient NAS searching algorithm. The recent Google work, NAHAS, it uses the weight sharing technique. So let's say we have these 3 search spaces and we have 3 algorithms. Usually, if you want to apply these 3 algorithms on these 3 search space separately, maybe you need 9 copies of code for each. For example, when you apply random search on the first search space, maybe you need 1,000 lines of code. And maybe when you apply, when you implement a Bayesian optimization to the search space, you need another 1,000 lines of code. So that's NAHAS. So basically, 3 by 3, you need 9,000 lines of code. But by using our symbolic programming, by using our PyGlove, after you have your existing training code, training your mobile net v2 on the ImageNet datasets, it's line 1 here. We call it the search space is static and search algorithm is none. Suppose you already have this training code and you want to upgrade your code to be a NAS algorithm using random search to search on the first search space. By using PyGlove, you only need 23 lines of code and you can get some accuracy gain. And then if you want to switch between random search and Bayesian optimization, you only need 1 line of code to switch between random search and Bayesian optimization. And so does that for the NAHAS, because that using this simple sample function, sample style, sample follow style, you just need to switch your algorithm from PPO to Bayesian and to NAHAS. And if you want to switch between different search space, from the static model, static mobile network 2 model, to the second search space, you only need 10 lines of code. And then if you want to switch both either S1 or S2 to S3, you only need 1 line of code. So that in sum, by using PyGlob, it lets you to use about 10 lines of code to switch between different search space and different search algorithms. It achieved the dynamic coupling between child program and the search space and search algorithms. This can let you implement your AutoML, your new AutoML algorithms very efficiently. And our previously mentioned two algorithms, AutoHAS and NAHAS, is also implemented based on PyGlob. So basically, this is all for today's presentation, and here is the takeaway. So for the future of AutoDL, automated deep learning, we believe that the symbolic programming-based infra is what you need. And also we think that the architecture search only is currently saturated. And if you want to have some new amazing results, you need to extend the scope of your architecture search to hyperparameter or to the hardware search. That's all. Thanks for listening. If you have any questions, please, we can have a discuss.